when we left off yesterday, we were talking about how Newton's first law is very important in terms of safety devices, okay, and things like that. So I actually wanted to kind of show you what that looks like a little bit, because I've got a few videos for the safety devices. Then we'll talk about some other applications of Newton's first law, and then we're going to talk about drawing free body diagrams. We already know how to draw vector diagrams, but free body diagrams, and then we will move on to Newton's second law, okay, which will be the next 2.5 weeks or so, because Newton's second law is huge. There are tons and tons of applications of it. Okay, so we were saying with Newton's first law that the application is that if you're in a car and it stops suddenly, what do you continue to do?
Go forward.
You continue to go forward, right? You continue to travel at a constant velocity, and that means straight forward. And so obviously that's the problem. We need to be restrained so that we don't encounter things that can hurt us. Okay, so obviously in your car, things are designed around protecting you, right? So you can kind of see here, I've got some crash test stuff, and you'll see the comparison between cars that do well and cars that don't, okay? If a car is going to do well in protecting you, what is it going to look like in terms of the movement of the dummy? Is there going to be a lot of movement or very little movement, or is there going to be mostly in one dimension as opposed to moving around? What do you think would be better?
Moving forward.
Yeah, if we can move, keep it in a straight line, there's a lot less chance for the twisting kind of spinal injuries, okay? And the less movement around in kind of all dimensions, there's a less chance of striking anything other than the airbag. Okay, I mean, obviously, in newer cars, you've got the curtain airbags and everything, so you're going to hit soft stuff everywhere if you're moving around, and that's the idea, okay, is to keep the movements as small as possible. Okay, the less movement we have, the less chance there is for a hyperextension of, the neck or something like that. That would be whiplash. All right, so that's what we'll be looking for here. So, difference between these two things. This is another thing that North American society gets very, very wrong. Okay? Oftentimes, people will say, I weigh this much. And then they give a number in either pounds or kilograms. Pounds and kilograms do not measure weight. They measure mass. Okay? When you tell someone that you are X many kilograms or X many pounds, you are telling them how much of you there is. Okay, which is your mass. Your weight is a force. It's how hard gravity pulls on your mass. The more mass you have, the more weight you have. Okay, they are related that way. But I can lose weight by going somewhere where gravity is less. I can't lose mass by doing that. Okay, mass is how much of me there is. The only way I lose mass or gain mass is to make more of me. Okay, so I either eat more or I eat less or I go to the gym or something. Okay, that's the only way to make more or less mass. And because I'm staying on Earth, my weight will go up or down accordingly. Okay, but weight is not just dependent on your mass, and thus it is not the same thing as mass. Okay, weight. Whoops. Weight is the force of gravity, Fg. And we calculate it by taking our mass in kilograms and multiplying it by 9.81, which we denote with a little lowercase g. Okay, so lowercase g stands for acceleration due to gravity. More often than not, that's going to be 9.81. Okay, so when I tell someone how much I weigh, I'm telling them how much force I would exert on them if I were to stand on their chest. Okay? Which is different than my mass. Okay? Mass and weight are very different. Okay? Because if I go to the moon, I'm going to have the same mass. But I'm going to weigh 1/6 of what I weigh here. Okay? Now, if you've seen moon landing footage, okay, the astronauts, they were wearing huge spacesuits. Okay, those spacesuits they had a mass of over 100 pounds each. Like they weighed as much or more as the person wearing them. So imagine walking around on Earth in one of these spacesuits. You're now 2 to 2.5 times heavier than you normally are because you're carrying around this spacesuit. But they look pretty nimble on the moon. They're jumping around and they're hopping all over the place because in the end, they weighed 1/6 of what they weigh here. They have the same mass, but even with the suit on, they still weighed less than they weighed on Earth. Okay? There's one shot, I couldn't find it, but there was one shot of a guy jumping, and he had like the whole suit on the moon, and he had like, it was an impressive vertical jump, wearing 2.5 times his normal mass. Okay? But he was able to, like this, like an impressive jump. Okay? And they actually found that walking normally on the moon was difficult because they weighed less than they were used to. And what ended up happening is, because when we walk, okay, like we actually push upwards a little bit. Some people do it more than others. Some people, you see them walking, they kind of go up and down a little bit. Okay, well, we always push down a little bit when we walk, which results in us moving upwards. Okay, well, when you do that on the moon and you weigh less than you normally do, it makes you a little bit off balance. Okay, and so they were finding that there was a risk of falling from just walking normally. So they ended up developing the shuffling kind of gait that they used on the moon, okay, to limit the amount of upward force they would exert so that they would be better balanced and not fall. Because if you fall and you hit your faceplate on a rock, you die, and that's bad. Okay? So they wanted to be as safe as possible. All right, so does the difference between weight, which is a force, and mass, which is how much of you there is, make sense? Okay, so that's the difference between weight and mass. We treat them like they're the same thing, but they're not. Okay, your weight is how heavy you are, and that's a force. Okay, we experience weight as a pressure, okay, or you know, like a pushing, or even a pulling. Okay, but mass is just how much of me there is. Okay, and I can only change that by making more or less of me. All right, so we just have to make sure we understand that. This is a formula that we're going to use actually quite a bit in Newton's second law because the force of gravity, or weight, is something we use often because it's always there. All right, so if we're thinking about Newton's first law, okay, and about inertia, okay, think of hockey. If a puck is just sitting on the ice and nobody does anything to it, it's just going to sit there. Okay? But once that puck is put in motion, if, let's say theoretically, the ice was frictionless, the puck's velocity would never change. Okay? It would just keep going at a constant velocity. Okay? Does that sort of make sense? Okay? Now, obviously, ice is low friction, but it's not frictionless. Things obviously do come to a stop and slow down on the ice. It's just limited. Okay? Same with curling. Okay? So if you throw the rock, okay, it slides down the ice. If the ice, let's say, is frictionless, which obviously it's not, then the rock's velocity doesn't change, and it travels in a straight line. Can you make the rock change direction in curling? Okay, and there's two ways to do that, right? You can either turn it as the person who threw it, so you can do an in-turn or an out-turn, I think that's the way it goes, okay, which imparts spin to the rock. Okay? Imparting spin to the rock changes the way it interacts with the ice surface and can lead to it changing direction. Okay? You can also change its direction by sweeping it. Okay? So if you've ever seen that done, okay, what they do is they, I don't know if you guys have ever seen what a surface of ice, an ice sheet in curling looks like, but it's not like a hockey rink. Okay? In curling, they actually take like a garden hose and they put it on that kind of like showery setting, and they just hold it up and they spray it, and you get these little kind of droplets landing on the ice and freezing on there. So it's actually rough to the touch. There's little bumps all over it from these little droplets of water that have landed on the ice and froze on there. So it's not smooth, okay, like a hockey rink. Okay, I mean, between every period in hockey, they go out and flood the ice to make it smooth. And in curling, they want the exact opposite. They want all these little bumps all over the place. So what happens is when they're sweeping, they put the broom down and they push really, really, really hard, and then there's enough friction there that it melts these little When you do that, you create a thin layer of water underneath or between the rock and the ice. When that happens on the road, between your tire and the road, what does it do? Yeah, it can cause you to hydroplane. It lowers the friction that's available for traction. Well, the same thing happens when you sweep. So if you sweep in front of the rock, you lower the amount of friction, so it'll travel further. Its speed will change less, and you can actually steer it if you're really good. And if you're a really good sweeper, you can sweep on just one side of the rock. It'll actually turn the other way, okay? Because you lower the friction on one side, friction is higher on the other, and it slows it down on one side, which causes it to turn. Okay? In the same way that if I'm walking along and I put my arm out, okay, and I'm walking normally, but my arm hits, look what happens to me. I turn in the direction that I'm slowing down, right? The other side of me didn't slow down, that side did, and it caused me to turn.
So is it true that when you're like skating on ice, you're on a thin layer of water on your skate between the ice and your skate?
I don't know the answer to that for sure, but it doesn't seem like that would be right, because you've got the two edges on the blade, right?
Right.
Like that's why you sharpen your skate, and those edges help you to cut into the ice
Right.
to create something kind of like leverage,
Right.
right? So I would have to think that it doesn't feel right that there would be enough friction, or at least fast enough for that to really work. It's more that ice is a low friction and you've got very little, you've got those nice sharp edges that you can slide along. It's possible, but it doesn't seem, I'd have to look into it.
Okay.
Yeah. Okay. But this is also why winter tires work the way they do, okay? The thing that makes things really slippery is when your tires start to spin, you get this melted ice, so you get water, a thin layer of it between your tires and the ice, and that lowers the friction even more. But the tread pattern on a winter tire has big blocks, big like traction blocks, okay? And on those blocks are these little zigzag patterns. If you've never seen it, have a look the next time, okay? There's all these little zigzag patterns, and they're called sipes, okay? And these sipes draw water away. Like they're very small slits, but under pressure, when your tire is on the ground, those sipes open just a little bit, and water is drawn into it because of the polar nature of water, and that removes it from the interaction between the tire and the ice, improving your traction. Okay, so that's actually what all those little grooves are for, is to pull any melted ice away, okay, to improve your traction. Okay? And winter tires are softer than summer tires, which allows their shape to change better, even in cold weather, for those sipes to work. You don't see those on an all-season tire or a summer tire because it's not necessary. Okay? In the summertime, you want a harder tire because the heat is going to be there, and that's going to soften it instead. Okay? It's why you don't want to run your winter tires in the summer. They're already soft. Above 5 degrees, they start to wear really, really quickly because they're so soft. That extra warmth causes them to wear very fast. So, don't leave your winter. I gotta make an appointment to get my winter tires off. It's like middle of March already. It's a good thing we had this conversation. Okay. All right, so does everyone kind of follow what that looks like? Okay. This is a big problem if you're an astronaut. If you're doing an EVA, that's an extravehicular activity, so you're in your spacesuit and you're outside of the space station or whatever, and you're not on a surface, so you're just out there floating in space. Once you get moving, how do you stop? You hit something, yeah. Or you use your maneuvering jets. They're called reaction control thrusters or reaction control systems. They're small little jets, basically, okay? And you can control them with a little switch. It's usually on a stick by the handle, by the glove, okay? And you can just move it around, and it'll activate different jets, okay? And those jets will, if you've seen The Martian, he uses them a little bit in The Martian, okay? And then he punctures his glove and flies like Iron Man. Okay, remember that scene? That's how they work. It's the escape of pressurized gas creates a force that can speed you up, slow you down, steer you, okay, which is like totally ludicrous that he would ever have been able to control what he was doing. Okay, but that's how they actually maneuver around. If you run out of pressurized gas for those jets, you no longer have any way to change your velocity. Flailing around in space doesn't do anything. doesn't even really do anything in air, okay? But if you have no way to change your velocity, you could theoretically just float away. Yeah, and there'd be nothing you could do about it, right? So, this is another one of those lessons where I got lots of things. Okay, so Newton's first law says an object at rest will remain at rest. Object traveling at a constant should be velocity, not speed. Okay, will continue to do so unless acted upon by a net force. So your net force is the unbalanced force. Okay, so in lots of cases, forces are balanced. If the forces are balanced, then the net force is 0. Okay, if the forces are not balanced, then there is this net force that is going to result in some change in velocity. Okay, so the net force is the vector sum of all of the forces, and net force is what leads to Newton's second law. Okay, so in this diagram right here, okay, I've got a book, okay, and there's a person pushing on the book with 20 newtons worth of force to the left. Friction is resisting with 18 newtons of force to the right. Okay, the vector sum of those two collinear vectors, right, so we got 20 and 18 is 2 newtons to the left. Okay, that's my net force, the vector sum of all the forces that are acting on the book. Now, they've missed a few forces. There's actually a couple of other forces that are acting on the book. Gravity and normal force. Okay, that would be the force of the table or whatever it's sitting on. But those two forces are balanced. They cancel each other out. The book isn't moving vertically. Okay, so they're not part of the net force. If I was doing the vector sum of all forces, I would then have gravity and normal force, but they would cancel each other out. They wouldn't be part of this. That sort of makes sense? If I was drawing a vector diagram, I drew everything tail to head, right? They canceled out because they go up and back. All right, so my net force is 2 newtons. That means there's an unbalanced force, and that book is going to accelerate to the left because of that net force. Okay? Now, Newton's first law can allow you to do a few kind of tricks, let's say. Anyone ever seen the magic trick where someone pulls the tablecloth out from underneath all the dishes? That's totally possible. And it relies on Newton's first law. It also relies on the right kind of dishes, the right kind of tablecloth, okay? And how you pull on the tablecloth. I've seen people who do this thing wrong so many times because they think it's all about flourish. Okay? So they grab the tablecloth and they do this. And they lift up. Okay? Well, once you lift up, you lift the whole tablecloth up and everything on the table gets upended. Right? If you want that to work correctly, what you have to do is you have to grab the edge of the tablecloth at the edge of the table and pull straight downwards. Okay? That way there's no upward component. It just slides out from underneath the dishes. You also need the right kind of tablecloth. You're not doing this with a cotton cloth tablecloth. Silk tablecloth, maybe. Okay? Even one of those like vinyl ones that you can get at the dollar store, okay, would be more slippery. You want something that's pretty slippery. Do you want the dishes to be light or heavy? Heavy. The heavier they are, the more inertia they have, the greater the tendency they have then to stay put, even when you pull the tablecloth out from underneath them. So I always tell people, like, if you're going to do this, don't use your mom's best china and crystal, even though the best china and crystal is going to be heavier than the dollar store plastic dishes that are definitely going to move along with the tablecloth. Okay, so if you're going to do this, practice with plastic dishes that have weight on them so that you get good at it before you try it with the expensive stuff. All right, another application, tearing toilet paper. Okay, so toilet paper's on a roll, okay? And if you want to unroll the toilet paper, you pull slowly on the end. But there's perforations, right? There's the sheets, individual perforations. If you want to tear it, you pull really hard. Then it tears at the perforation because there's enough mass on the roll that its inertia is that it stays put. So it's not enough force to unroll the roll, but it's enough to tear the perforation. If I pull slowly, okay, then I don't exert enough force to tear the perforation, and I unroll the roll. Yeah? See, physics is everywhere. I told you you're never going to look at the world the same. Okay? Everything looks different. All right, now, when does that work best? Full roll or nearly empty roll? If I just want to tear it off real quick, full roll or empty roll? Full, more mass. Okay? If you're getting near empty, when you do that and there's not enough mass, there's not enough inertia left on the roll, and the thing will unroll. On the bright side, there's not that much left on the roll, so you won't have a huge mess to clean up. Okay? And that's also why you're supposed to put the toilet paper on a certain way so that it's not unrolled. There's a proper way to hang toilet paper. It's overhand. It's actually one of my wife's pet peeves. She actually has in our bathroom a picture of the original patent for toilet paper on a roll, and it indicates that it must be hung this with the overhand. So it's overhand. Our friends come over and they reverse it just to mess with her. I don't. I'm smart. Okay. All right, so inertia and mass, okay, the more mass you have, the more inertia you have, the more your tendency is to stay put. Okay, we've seen lots of examples of that thus far. Okay, and that's the same thing. Okay, we talked about this the other day as well, how your seatbelt works, how it relies on Newton's first law. Okay, if the car stops suddenly, the pendulum swings forward because it's trying to obey the Newton's first law, which causes the ratchet wheel to lock into place. All right. Now, free body diagrams, and we'll end with free body diagrams here. In this unit, your givens are going to look different than they looked in the last unit. In the last unit, givens were like, oh, I'll write VI and VF and equals. In this unit, your givens are very often going to be a diagram. Not the vector diagram, but a free body diagram. Okay? A free body diagram indicates where the forces and which forces are acting on a particular object. So if I had this example of the car, I wouldn't draw a car. Free body diagrams don't have to be fancy. Okay? Free body diagram needs to be a block. Okay? A block that represents whatever the object is. And you write its mass inside. So I don't know, let's just say the car is 1,500 kilograms. Okay? Now, if that car is slowing down, okay, so maybe it's run out of gas. The engine is no longer powering it forward. Okay? There are going to be 4 forces acting on the car. Okay? There's going to be the force of gravity. There's going to be the normal force. That's the force of the road pushing back against gravity. These 2 forces are what? Equal. Okay? All right, and in this case they'd be equal, as long as the road is level. Right? If it was inclined or something like that, then they wouldn't be equal. Okay, and then because the engine isn't running, there's 2 things bringing this thing to a stop. Air resistance and friction. Okay, so F of air, so the force of the air and the force of friction, both acting backwards. Okay, so that's my free body diagram. I now know what forces are acting on the car, and if I was a little further along in the unit, I'd be able to either calculate them, or if the question actually gave them to me, oh, okay, we got them actually. Okay, so air resistance, there's, oh, okay, so I drew this wrong. Let's just, air and friction. Okay, so they're saying this one's 2,500 newtons, and this one is 500 newtons. Okay, and then gravity, so we'd have 10,000 newtons here. Well, it wouldn't be for this, it would be a different number because I picked a different mass. But okay, these 2 would offset regardless. So from my free body diagram, all I use that for is to identify the forces and figure out which way they're going. From there, I go to a vector diagram. Okay, so a vector diagram of this would be gravity, normal force, so they cancel. I wouldn't even really draw those, would I? Like if they cancel each other, there's really no point. Okay? And then I would have 500 and my net force then would be how much? 3,000 newtons backwards. Okay, so free body diagram is pretty straightforward. It just helps us get the forces identified, like writing down givens. And then we can go to a vector diagram from there. All right, so tomorrow we are going to start on to Newton's second law. And then you'll see all the places, your world will change. It's everywhere. All right, no quiz tomorrow either. Okay, there's nothing to quiz you on yet. There's no problem solving for Newton's first law. No quiz tomorrow.